Picture the ancient Egyptians at work, thousands of laborers hauling massive stones under the blazing sun, carving hieroglyphs with copper chisels, shaping history with what we assume were primitive tools. It's an image we've all seen in documentaries and history books, one that suggests immense human effort but relatively simple technology. But what if I told you that story is incomplete? What if the real tools they used were far more advanced, more precise, and more mysterious than anything we've given them credit for? For generations, we've underestimated the ingenuity of these master builders. We marvel at the pyramids, the temples, the obelisks, monuments that have stood for millennia with near-perfect alignment and breathtaking craftsmanship, yet we still imagine them being built with little more than ropes, ramps, and rudimentary copper instruments. But hidden in the sands of time are clues to a different truth. The ancient Egyptians didn't just possess simple tools. They had technology so sophisticated, so precise, that it rivals some of the engineering marvels of our own era. These weren't just artifacts, they were instruments of genius, designed with an understanding of mathematics, astronomy, and material science that we are only beginning to grasp. Today, we're going on a journey deep into the forgotten workshops of ancient Egypt, uncovering the tools that have been lost to history, tools that challenge everything we thought we knew about this incredible civilization. From mysterious drilling devices that cut through granite like butter, to astonishing measuring instruments aligned with the stars, we'll explore how these innovations made the impossible possible. This isn't just a story about how they built what they built. It's a revelation about who they were: visionaries, scientists, artists, and how their legacy of ingenuity still echoes today. So settle in, because what you're about to discover will change the way you see ancient history forever. When we try to picture an ancient Egyptian artisan, the mind often conjures a solitary figure with a simple hammer and a copper chisel. But that image is a dramatic oversimplification. The reality was far more complex and infinitely more fascinating. These master builders operated not with a mere handful of implements, but with a comprehensive and highly specialized toolkit, one that could rival a modern master craftsperson's workshop. Their array of instruments was carefully designed for every single task, every specific material, and every minute detail of their monumental projects. To truly appreciate their achievements, we need to move beyond hammers and chisels and explore the full, sophisticated spectrum of their technology, which we can break down into 4 key categories. First, let's consider the measuring and layout tools. The breathtaking precision of the pyramids doesn't come from guesswork, it comes from exacting measurement. Artisans use tools like the merkhet, an ingenious instrument that functioned like an ancient theodolite. By aligning 2 of these devices with the North Star, they could lay out the cardinal directions with an accuracy that still astonishes surveyors today. They employed simple but effective plumb bobs for perfect verticals, crafted from stones tied to string, and used leveled mud beds and water-filled trenches to ensure their foundations were perfectly flat across vast distances. This obsession with measurement was the absolute bedrock of their architectural genius. Then came the cutting and shaping tools. While copper chisels were indeed used for softer stones like limestone, they would have been useless against the granite and basalt used for sarcophagi and obelisks. For those immensely hard materials, they employed a technique called pounding. They used hand-held balls of even harder stone like dolerite to literally pulverize the granite grain by grain, a painstaking process that resulted in incredibly smooth, flat surfaces. Saws also existed, but not as we know them. They were copper blades without teeth, used with a slurry of abrasive sand and water. The sand, typically quartz, did the actual cutting as the worker sawed back and forth, slowly grinding through even the toughest stone. Perhaps the most mysterious category is their drilling and boring equipment. We have found core samples drilled into granite that display spiral grooves and a feed rate, the speed at which the drill bit advanced, that is almost identical to modern diamond-tipped drills. How was this possible with primitive technology? The evidence suggests they used tubular drills, likely made of copper, again employing that abrasive quartz sand slurry. The tube would be rotated, probably with a bow drill mechanism, and the abrasive paste would slowly wear away a perfect, circular core from the solid stone. The precision of these holes, some several inches deep, is a silent testament to a technique we are still struggling to fully replicate. Finally, we have the finishing and polishing tools. The mirror-like sheen on statues and the glass-smooth interiors of granite coffins weren't achieved by accident. After the brutal work of pounding and sawing, artisans moved on to abrasives. They used progressively finer grades of sand, from coarse quartz to powdery emery, often rubbing them with flat stones or leather pads to achieve that legendary, flawless finish. This meticulous attention to detail, this refusal to leave any surface untreated, is what transformed massive blocks of stone into objects that feel alive, even to this day. This entire toolkit, from the star-aligned merkhet to the finest polishing sand, reveals a civilization that didn't just brute force its way to greatness, but engineered it with patience, intelligence, and an unparalleled mastery of their craft. Now, let's zoom in on one of the most critical and overlooked instruments in that entire toolkit, a device that proves their brilliance wasn't just in how they cut stone, but in how they saw the universe itself. This is the story of the merkhet, the ancient star clock of the pharaohs. At first glance, this tool seems almost laughably simple. It was typically just a narrow, forked stick made from a palm leaf rib with a vertical slit cut into it, paired with a plumb bob weight hanging from a string. You wouldn't look twice at it if you saw it lying in the sand, but in the hands of a skilled Egyptian astronomer priest, this humble pair of tools became one of the most sophisticated surveying instruments in the ancient world. Its primary function was to create perfect alignments by tracking the movement of the stars. Imagine a clear desert night. A priest, known as an observer, would set up two of these merkhets some distance apart, aligning them so that the plumb line hung perfectly within the slit of the sighting bar. He would then carefully watch a specific circumpolar star, one that never sets below the horizon, as it crossed the meridian, the imaginary north-south line in the sky. By noting the exact moment the star passed through the aligned sights of both merkhets, he could establish a true north-south baseline with an accuracy of within a fraction of a single degree. This wasn't just a rough guess, it was a precise scientific measurement. The Great Pyramid of Giza is the ultimate testament to its accuracy, aligned to true north with an error of just 1/15 of a single degree, a feat of engineering that seems almost impossible for its time. But the merkhet's genius didn't stop there. It also functioned as a remarkably accurate clock. The same priest could use a single merkhet to track the transit of other stars across the night sky. By using a clepsydra, or water clock, to measure the time between the transits of different stars, he could effectively chart the passage of the hours throughout the night. This was crucial for timing religious ceremonies that were required to begin at specific, astrologically significant moments. It connected the rhythm of their rituals directly to the cosmic dance overhead, blending practical timekeeping with profound spiritual belief. The true marvel of the merkhet lies in this beautiful intersection of simplicity and complexity. It required no advanced metallurgy or intricate moving parts. Its power came not from the tool itself, but from the deep, accumulated knowledge of the person using it, an understanding of astronomy, geometry, and the predictable patterns of the cosmos that had been honed over centuries. This simple forked stick and a dangling weight were the keys that unlocked the heavens, allowing the Egyptians to anchor their most sacred structures to the stars themselves, creating a landscape on Earth that mirrored the perfection of the night sky. While the merkhet allowed the Egyptians to align their monuments with the heavens, another tool, equally humble in appearance, was responsible for bringing those celestial perfections down to Earth. This was the bay, the ancient Egyptian level, and it was the key to achieving one of the most mind-boggling feats of their engineering, the incredible, almost supernatural flatness of their construction sites. If you stand at the base of the Great Pyramid today and look across the 13-acre foundation, you are standing on a man-made limestone platform that is flat to within just over 2 centimeters. That's flatter than the floor of a modern concert hall, and it was accomplished over 4,000 years ago. This wasn't a happy accident, it was the direct result of the bay. The design of this tool was a masterpiece of simplicity. Picture a narrow, shaped wooden frame, much like a modern carpenter's level, but without the glass vial. From the apex of the A, right at the central point, a string would be tied, and from that string hung a simple plumb bob. The genius was in the marking. A precise line was scored into the wood on the crossbar at the base of the A, directly below the point where the string was attached. The entire function of the tool relied on a single, perfect relationship. When the crossbar was perfectly level, the hanging string would align exactly with that scored mark. Using it was a methodical process. A worker would place the bay onto a stone block that had been roughly leveled. He would then watch the string. If it drifted to one side of the mark, that side of the block was too high. He and his team would then painstakingly pound, chip, and sand the high spots down, checking and rechecking with the bay until that string hung in perfect alignment with the mark. Once that single block was level, it became the reference point for the entire site. But how do you ensure that a reference block hundreds of meters away is on the exact same plane as the one you're working on? The Egyptians solved this with a system of water-filled trenches. They would dig a network of shallow channels across the bedrock of the entire site and fill them with water. Because water always seeks its own level, the surface of the water in every trench would be exactly level. They then set measuring rods into the water at regular intervals, marking a fixed height above the waterline. This created a site-wide grid of constant elevation points. A worker could place his bay on a stone anywhere on the site, and by checking it against the nearest water trench marker, he could be absolutely certain that his block was perfectly level with every other block on the foundation. This combination of the simple hand tool and the large-scale hydrological system is what allowed them to achieve such breathtaking accuracy over such an immense area. It demonstrates a profound understanding of basic physics and a level of project management that would be impressive even by today's standards. The bay was more than just a tool. It was the physical manifestation of their unwavering commitment to perfection, ensuring that the first course of stones, and every one that followed, was laid on a foundation as flawless and steady as the earth itself. While the bay brought celestial perfection down to the earth, the ancient Egyptians also looked directly to the sun to organize their world, mastering time itself with nothing more than light and shadow. Their solar timekeeping devices were marvels of pragmatic innovation, transforming the most fundamental daily phenomenon, the sun's journey across the sky, into a reliable, measurable system. The earliest and most personal of these tools was the shadow clock, a portable timepiece for the elite. Imagine a simple T-shaped instrument. The horizontal bar had a raised end, and the vertical bar cast a moving shadow along a scale marked with 5 unequal hours. As the morning progressed into afternoon, the shadow would shorten and then lengthen again, dividing the daylight period into manageable segments. This wasn't about precision to the minute, but about structuring the day for administrative duties, religious rites, and the rhythm of labor. It was timekeeping made tangible, a personal sundial one could hold in their hand, but their ambition didn't stop at small, portable devices. The Egyptians saw the very fabric of their architecture as an opportunity to merge function with cosmic order. This is where the humble gnomon, the shadow-casting element of a sundial, was transformed into something monumental. The mighty obelisks that stood before temple pylons were not merely symbols of power or petrified sunbeams. They were giant, public timekeeping instruments. Each towering monolith, sheathed in glittering electrum to catch the first and last rays of the sun, functioned as the world's largest sundial needle. Its immense shadow, sweeping in a great arc across the temple forecourt, provided a communal clock for the entire city. Priests and pharaohs could mark the hours of ceremonies, while the public could organize their day by the slow, majestic crawl of this stone shadow. The true genius of this architectural timekeeping, however, was revealed during the solstices. The Egyptians were keenly aware of the solar cycle, and the obelisk was a perfect tool for observing its extremes. At the summer solstice, the sun reaches its highest point in the sky, casting the shortest shadow of the year. At the winter solstice, the sun is at its lowest, creating the year's longest shadow. By carefully observing and marking the precise endpoints of the obelisk's shadow at noon on these pivotal days, Egyptian astronomers could accurately determine the length of the solar year. This knowledge was absolutely critical. It anchored their 365-day calendar, which in turn governed the all-important annual flooding of the Nile, the event upon which their entire agricultural cycle, and therefore their survival, depended. The obelisk was far more than decoration. It was a central pillar of their scientific, religious, and economic world, a permanent observatory that connected the heavens to the harvest, and the divine to the daily lives of every Egyptian. Yet for all their mastery of alignment, leveling, and timekeeping, perhaps the most enduring and perplexing mystery of ancient Egyptian technology lies not in how they laid stones, but in how they cut them. We've all seen the iconic images of artisans with copper chisels, but that picture completely falls apart when we confront the evidence of their work on the hardest stones. How did a civilization, we're told, had only simple copper tools manage to drill perfectly cylindrical holes through solid granite? How did they hollow out the interiors of stone vessels with necks narrower than their shoulders? The answers point to a forgotten technology so effective, its results still baffle engineers today. The proof is locked inside the stone itself, in the form of core samples drilled out thousands of years ago. The most famous example is a core of red granite housed in the Petrie Museum in London, collected by the renowned archaeologist Sir William Flinders Petrie himself. To the untrained eye, it might look unremarkable, just a cylinder of dark stone, but to an engineer, it's an absolute bombshell. This core was drilled from a much larger block, and the grooves spiraling around its surface tell a revolutionary story. They are continuous, uniform, and incredibly deep, indicating a feed rate, the speed and pressure at which the drill advanced into the stone. That is shockingly consistent. This isn't the jagged, irregular scarring you'd expect from a primitive tool being shoved and twisted by hand. This is the mark of a tool that was rotating at a high, steady speed under immense, constant pressure. The precision is such that the grooves are almost identical to those left by a modern diamond tip drill core bit. So how was this possible? The technology behind this marvel was the tubular drill. Imagine a thin tube, likely made of bronze or a hardened copper alloy. This tube would be fixed to a spindle, probably rotated by a bowstring mechanism that allowed for sustained, rapid spinning. But the tube itself wasn't the cutting agent. The real magic was in the slurry. Workers would pour a wet mixture of quartz sand, one of the hardest natural abrasives on Earth, into the shallow hole started by the tube. As the tube spun, the abrasive sand particles trapped between the metal and the granite were forced against the stone, grinding it away micron by micron. The tube acted like a cookie cutter, but instead of slicing, it was grinding a perfect circular kerf, or channel, into the rock, leaving a solid core in the center that could later be broken free and removed. This explains the mysterious spiral grooves perfectly. They are the fossilized record of the individual abrasive particles being dragged in a continuous path under tremendous pressure. The depth and consistency of these grooves suggest the drill was not only spinning fast, but was also being weighted or levered down with a force that would be incredibly difficult to achieve with human muscle power alone. This has led many researchers to speculate that the Egyptians must have developed some form of mechanical advantage, perhaps a weighted lever arm or even a simple capstan mechanism, to apply the massive, unwavering downward force required. This wasn't a handheld tool. It was likely part of a larger, stabilized apparatus. The implications are staggering. It means the ancient Egyptian workshop contained machinery designed for high-speed, precision drilling operations that we would only reinvent millennia later. This single granite core is a silent, stony witness to a level of technological sophistication that forces us to completely rewrite the story of their capabilities. If the tubular drill showcases their mastery of rotary motion, then their sawing techniques reveal a breathtaking command of linear, sustained force. We're not talking about saws as we know them, metal blades with sharp teeth designed to bite and cut. The ancient Egyptians, when faced with blocks of granite and basalt that would instantly blunt any copper tooth, engineered a far more brilliant and relentless solution: the abrasive saw. These were massive, straight-edged blades, often several meters in length, made from sheet copper or bronze. They had no teeth at all. Their cutting power came not from the metal itself, but from what they dragged along with them: a slurry of water and quartz sand, one of the hardest natural minerals on the planet. The process was a monumental exercise in patience and coordinated labor. A massive granite block would be firmly secured in place, often in a quarry or a workshop. Teams of workers would then manhandle the large, toothless saw blade, pulling it back and forth across a line marked on the stone's surface. With each stroke, assistants would pour more of the abrasive quartz sand slurry into the cut. The sand particles would become embedded between the metal blade and the stone, and as the blade moved, these microscopic bits of quartz would act like countless tiny, hard chisels, grinding away the granite at a glacial but utterly relentless pace. The metal saw blade was merely a delivery system, a vehicle for transporting the true cutting agent, the sand, back and forth across the same precise line, hour after hour, day after day. The sound would not have been a high-pitched screech of metal on stone, but a low, gritty, grinding rumble, a testament to sheer, persistent abrasion. The scale of this operation is almost incomprehensible. To cut through a single massive obelisk or a thick sarcophagus lid could have taken months, or even an entire year, of constant, grueling labor. The manpower required was immense. It wasn't just the men on the saw. It was the teams mining and crushing the quartz sand, the workers hauling water, and the overseers ensuring the blade stayed perfectly on its line. This was an industrial process, a systematic and well-organized assault on some of the hardest materials on Earth, powered by human muscle and guided by unwavering precision. Perhaps the most stunning evidence for this technique isn't in a finished monument, but in a magnificent failure: the unfinished obelisk in the Aswan granite quarries. This colossal obelisk, which would have been the largest ever erected had it not cracked during its extraction, remains partially attached to the living bedrock. It is an open-air museum of ancient Egyptian stoneworking technology, and its sides are a textbook of tool marks. Most tellingly, along its base and sides, you can clearly see long, straight, parallel grooves, the unmistakable scars left by these massive abrasive saws. These channels show where teams were in the process of separating the finished obelisk from the quarry wall, painstakingly grinding their way through the granite. The obelisk's abandoned state allows us a frozen moment in time, a raw and powerful snapshot of the sawing method caught in action. The grooves are deep, straight, and uniform, proving this was no haphazard hacking but a controlled, deliberate, and highly skilled operation. It stands as eternal proof that their greatest tool was not copper or bronze, but an unshakable resolve to conquer stone through intellect, innovation, and inexhaustible patience. While the saws and drills conquered stone, another tool shaped the very soul of Egyptian craftsmanship, turning raw timber into the objects of daily life, majesty, and the afterlife. This was the adze, a tool so common it might be easily overlooked, yet so vital and sacred that it became a symbol of creation itself. Unlike the massive industrial saws, the adze was a personal instrument, an extension of the artisan's arm. Its design was beautifully straightforward. A sharp, curved blade made of copper or bronze was mounted at a right angle to a wooden handle. This L shape gave it a unique swinging motion, allowing a worker to pull thin, controlled shavings of wood towards himself with incredible precision. Its utility was absolutely boundless. In the hands of a shipwright, the adze was used to hollow out the massive hulls of the great wooden barges that sailed the Nile. For a carpenter, it shaped the beams and planks that roofed temples and palaces. Furniture makers relied on it to carve the elegant legs of chairs, the curved arms of thrones, and the intricate panels of chests. Even the funerary industry depended on its keen edge to craft the smooth, perfectly fitted lids of coffins and the elaborate sarcophagi that would protect the dead for eternity. From the grandest construction project to the most delicate inlay, The adze was the go-to tool for shaping wood. Its distinctive curved cut marks can still be found on countless wooden artifacts, a permanent signature of the craftsman's skill. But the adze's importance transcended the workshop. It was imbued with a profound spiritual significance, directly linked to Ptah, the god of craftsmen, builders, and creation. In Egyptian mythology, Ptah was the divine architect who conceived the world in his heart and then brought it into existence through his spoken word. He was the patron of all who made things, and the adze was his sacred instrument. This connection elevated the tool from a simple implement to an object of power. We see this most powerfully in the opening of the mouth ceremony, the crucial ritual performed on a mummy to restore its senses for the afterlife. A priest would use a ceremonial adze to touch the mouth and eyes of the deceased statue or mummy. This act wasn't merely symbolic. It was believed to magically animate the spirit, allowing it to see, speak, breathe, and eat in the next world. The adze, therefore, was not just a tool for shaping wood. It was an instrument that could shape destiny, bridging the gap between the physical labor of the craftsman and the divine act of creation. It stands as a perfect symbol of ancient Egyptian culture, where the practical and the spiritual were seamlessly woven together, and where even the most common tool in a kit could hold the power of a god. And yet, for all the sophistication of their saws and drills, the tool most synonymous with the Egyptian artisan remains the humble chisel. We often picture them as simple copper bars, and for the earliest periods and softest stones, that's exactly what they were. But the story of the Egyptian chisel is not one of a static, primitive tool. It is a tale of continuous adaptation and material innovation, a direct response to the increasingly ambitious projects the pharaohs demanded. Their journey with this tool reveals a deep, practical understanding of metallurgy and a willingness to evolve their technology to meet any challenge. In the early dynastic periods, working primarily on soft limestone and sandstone, a basic copper chisel was sufficient. Artisans would heat and hammer native copper into a flat, beveled edge, haft it into a wooden handle, and go to work. These early chisels were relatively soft and would blunt quickly, but the soft stone was forgiving. The real challenge emerged when the architectural ambition of the kingdom grew, and builders began to incorporate immensely hard stones like granite, basalt, and quartzite for sarcophagi, statues, and obelisks. A soft copper chisel would be completely useless against these materials, bending and deforming upon first impact. This technological barrier forced a breakthrough, the development of hardened copper alloys. Through experimentation, Egyptian metallurgists discovered that by adding arsenic or later tin to copper, they could create a much harder, more durable metal bronze. This was a revolutionary advancement. A bronze chisel could hold a sharper edge for far longer and withstand the tremendous impact forces needed to fracture hard stone. The process of using these chisels was a symphony of controlled violence. A stone carver would position the sharp edge of the chisel against a marked line on the stone. His assistant, or sometimes the carver himself with his free hand, would then strike the butt of the chisel's handle with a wooden mallet. The mallet was crucial. Its relatively soft wood transferred the force of the blow without splintering the metal handle or causing the kind of damaging rebound a harder hammer would create. The technique wasn't about slicing the stone, but about exploiting its natural fracturing properties. The carver wasn't just hitting randomly. He was directing a series of precise, percussive blows to create a controlled shock wave that would travel through the stone, following the grain and popping off small, predictable flakes. By working in a line, they could gradually create a deep groove or even split a massive block along a perfectly straight line. You can still see the evidence of this today in the quarries at Aswan, where thousands of these small, precise chisel marks line the trenches around the unfinished obelisk, showing exactly how they planned to separate it from the bedrock. But this hard work came at a cost. Even the toughest bronze chisel would dull, deform, and even curl over at the edge after sustained use. This meant that the workshop was never silent. Alongside the constant tapping of mallets on chisels was the ringing of hammers on metal from the tool sharpening station. Smiths would constantly have to reheat, rehammer, and resharpen the blunted tools, a cyclical and time-consuming process that was absolutely essential to keep the work progressing. This endless cycle of use and renewal speaks volumes about their methodology. It wasn't about having an indestructible tool. It was about having a resilient system, a continuous workflow that acknowledged the limitations of their materials and built the process of maintenance directly into the rhythm of construction. The chisel, in its evolution from soft copper to hardened bronze, embodies the pragmatic, problem-solving heart of Egyptian engineering, proving that their greatest strength was not in having magic tools, but in possessing the relentless ingenuity to make the tools they had work for them. Yet if the chisel and mallet represent the hammering force of Egyptian industry, another tool harnessed a completely different kind of power, the transformative energy of rapid, sustained rotation. This was the bow drill, a deceptively simple device that may be one of the most versatile and underappreciated tools in all of human history. In its most basic form, it consists of just 4 components: a spindle, a mouthpiece, a bow, and a drill bit. The spindle is a straight stick, pointed at one end. The mouthpiece, often made of stone or wood with a small cup-shaped depression, is held in the user's mouth to steady the top of the spindle. The bow is a curved piece of wood with a loose string tied to each end, and the drill bit, attached to the business end of the spindle, could be anything from a sharpened piece of flint to a copper point. The magic is in the motion. The user would wrap the bowstring once around the spindle, place the pointed end into a small starter hole in the material to be drilled, and then steady the top of the spindle with the mouthpiece. Then, with one hand moving the bow back and forth in a continuous sawing motion, the string would spin the spindle at incredible speeds. This simple mechanism converted a short, back and forth movement into a continuous, high-speed rotation, a principle of mechanical advantage that is still used in machinery today. Most people associate this tool with its most dramatic function, starting fires. The friction generated by the spinning wooden spindle tip pressed into a dry wooden fireboard creates heat, then smoke, and finally a glowing ember that can be coaxed into a flame. This was undoubtedly a vital use, a portable technology for light, warmth, and cooking. But to focus only on fire is to miss its true revolutionary impact within Egyptian craftsmanship. The bow drill was, in essence, the ancient world's power drill, and its bit was interchangeable. By fitting the spindle with a hardened copper point instead of a wooden one, a craftsman could drill into materials far harder than wood. This is where its precision comes into play. We have countless examples of its work: tiny, perfectly round holes drilled through delicate carnelian and amethyst beads for necklaces, precisely bored holes in furniture joints for dowels that held chairs and tables together for centuries, and even holes drilled into stone tablets and obelisks, likely for inlaying other materials or for attaching decorative elements. The control offered by the bow and mouthpiece allowed for an astonishing level of accuracy. The user could apply gentle, consistent pressure and maintain a steady speed, allowing the abrasive copper tip, often aided by a sprinkle of quartz sand, to grind its way through the hardest stone with meticulous care. Perhaps the most startling evidence of this precision, and the tool's surprising versatility, comes not from a workshop but from the mouths of the dead. Examinations of mummies have revealed evidence of sophisticated dentistry, including drilled teeth. In some cases, small holes have been found drilled into the jawbone, likely to drain painful abscesses. In others, gold wire was used to bridge gaps or stabilize teeth, a technique that would have required incredibly delicate drilling to avoid shattering the enamel. The tool capable of such fine surgical work, almost certainly a bow drill with a tiny, specialized bit. This transforms our image of the tool from a rough fire starter to an instrument of delicate medicine. It was a technology that scaled from the monumental helping to start the fires that may have hardened the tips of massive drilling tools, down to the microscopic, capable of operations that required a steady hand and an exacting touch. The bow drill embodies the Egyptian genius for adapting a simple concept to an endless array of challenges, proving that their greatest innovations often lay not in complexity, but in the masterful application of fundamental principles. While the bay level guaranteed that every stone sat perfectly flat, creating a stable horizontal plane. Another equally vital tool was working to ensure that the walls rising from that foundation were just as flawless in the vertical dimension. This was the plummet, or plumb bob, a tool of such elegant simplicity that its basic design has remained virtually unchanged for 5,000 years. In essence, it is nothing more than a weight, often a symmetrical stone carved into a conical or teardrop shape, suspended from a long, taut string. The immutable law of gravity does all the rest, ensuring that the string always points directly toward the center of the Earth, defining a perfect vertical reference line against which anything can be measured. For the ancient Egyptian builder, this humble tool was absolutely indispensable. As courses of masonry rose higher and higher on a pyramid face or a temple wall, even the slightest deviation from true vertical would be magnified, leading to instability, misaligned corners, and a structure that was fundamentally unsound. The plummet was their safeguard against this. A craftsman would hold the end of the string at the top of a newly laid course of stones, allowing the weight to hang freely just in front of the wall's surface. He would then simply measure the gap between the string and the wall at both the top and the bottom. If the wall was perfectly plumb, that distance would be exactly the same from top to bottom. Any variation meant the wall was leaning in or out, and the masons would have to carefully adjust the next course of stones to correct the error. This process was repeated thousands upon thousands of times across every single face of every major structure. It was a constant, meticulous act of verification, a ritual of precision that ensured the towering walls of Karnak or the smooth, sloping sides of the Great Pyramid maintained their intended alignment as they reached for the sky. The true genius of their building system, however, lies in how they integrated these tools. The bay level and the plummet were never used in isolation. They were part of a continuous feedback loop of measurement. The bay ensured the horizontal plane was true, which provided a stable, level starting point from which to take vertical measurements with the plummet. In turn, a perfectly plumb wall ensured that the corners were straight and the angles were sharp, which was critical for the next level to be laid perfectly flat once again. This symbiotic relationship between the two tools is the secret behind those breathtakingly precise right angles found in Egyptian architecture. A builder could use his bay to establish a true horizontal line on a stone block. Then, using his plummet, he could mark a perfect vertical line at a 90-degree angle to it. This fundamental mastery of right angles allowed them to create not only the square bases of pyramids, but also the vast, orderly columned halls of temples, where hundreds of columns needed to be perfectly aligned in both directions. The sheer scale of this achievement is staggering when you consider the manual process. There were no laser levels, no digital theodolites, just the human eye, a weighted string, and an unwavering commitment to geometric perfection. The plummet, in its quiet gravity-driven certainty, was their unwavering guide, a constant reminder that while their ambitions reached for the heavens, their true foundation was always the immutable pull of the earth itself. But of course, the chisel was only one half of a perfect partnership. That sharpened metal edge would be utterly useless without its other half, the tool that provided the driving force, the controlled impact, the essential energy to make the cut. This is the story of the mallet, the humble, often overlooked hammer that was the absolute heartbeat of the Egyptian workshop. While we rightly marvel at the intricate artifacts left behind, we rarely pause to consider the symphony of precise impacts that created them. Every chip in the stone, every carved hieroglyph, every shaped piece of wood began with a strike, and the character of that strike was determined by the mallet in the worker's hand. The ancient Egyptian toolkit featured a surprising variety of mallets, each meticulously designed for a specific task and material. At the most basic and brutal end of the spectrum was the stone pounder. These were not sophisticated tools. They were often simply a hard, rounded river cobble, like a ball of dolerite, that fit comfortably in the palm. In the quarries, especially during the initial stages of extracting a massive block like the unfinished obelisk, teams of workers would use these stone pounders to literally pulverize the granite. They wouldn't strike a chisel, they would strike the stone itself, pounding along a marked line to create a deep trench by sheer, relentless force. This was brute strength work, and the tool reflected that, a heavy, durable mass designed to withstand crushing impact and transfer all its energy into breaking the stone. But inside the finer workshops, where sculptors brought statues to life and carpenters fitted joints with hair's width accuracy, a completely different kind of mallet was required. Here, the tool of choice was the wooden mallet, and its design was a masterpiece of ergonomics and physics. Crafted from a dense, hard wood like acacia or tamarisk, these mallets were carefully shaped. Many had a barrel-shaped head, a form that distributes weight evenly and allows for a comfortable, balanced swing. The handle was often offset or set at an angle that felt natural in the grip, reducing fatigue during long hours of work. The critical difference between this and a stone hammer is in the material. Wood is comparatively soft. When a wooden mallet strikes the butt of a bronze chisel, it creates a very different kind of impact than a stone hammer would. This difference was everything. It was the key to control. A stone hammer striking a metal chisel creates a sharp, high-impact shockwave. This is terrific for breaking rock in a quarry, but it's disastrous for fine work. That sudden, brittle impact can easily shatter a valuable piece of semi-precious stone being carved into a necklace amulet, splinter a delicate wooden inlay, or even worse, cause the hard bronze chisel to rebound violently and chip its own carefully sharpened edge. A wooden mallet, however, creates a softer, duller, more percussive thud of an impact. It's a force that is more absorbed and less jarring. This allows the carver to direct the energy of the blow down the length of the chisel and into the workpiece in a more controlled way, letting the tool's edge do the cutting rather than relying on explosive force. The master craftsman's skill lay in his intimate understanding of this partnership. He knew exactly how hard to swing his specific mallet to achieve the desired result. A lighter tap would produce a fine flake for detailed facial features on a statue. A firmer, fuller swing would remove larger chunks to rough out a basic shape. He developed a rhythm, a constant tap-tap-tapping that was the soundtrack of creation in ancient Egypt. This wasn't mindless pounding. It was a conversation between the artisan, his mallet, and his chisel. The mallet was his mediator, translating the force of his arm into a language the chisel could understand and apply with precision. Without the right mallet, even the sharpest chisel was just a piece of metal. But together, they became an extension of the artist's will, capable of either roughing out a colossus or etching the feather of a god onto a scarab beetle with breathtaking delicacy. But how could an empire build with such flawless precision across hundreds of miles and centuries without a single, universal standard? Imagine a master builder in Thebes and an architect in Memphis needing to ensure that the blocks they crafted would fit together perfectly for a pharaoh's new temple. They couldn't simply send a blueprint with measurements. They needed a shared language of length, a system so intuitive and reliable that it could transcend distance and time. The ancient Egyptians found this solution not in complex machinery, but in the most accessible instrument imaginable, the human body itself. Their entire system of measurement was a brilliant, anthropomorphic creation, using the proportions of the pharaoh, the living god on earth, as the literal benchmark for building a kingdom. The foundation of this system was the digit, roughly the width of an adult's finger. 4 digits made one palm, the width across the hand without the thumb. 7 palms laid end to end created the most important unit of all, the royal cubit, the distance from the pharaoh's elbow to the tip of his outstretched middle finger. This wasn't a vague approximation. The royal cubit was a precisely defined unit of about 52.3 centimeters. This choice was deeply symbolic, rooting the very scale of their architecture in the divine authority of the king. Every temple column, every pyramid base, every corridor in a tomb was therefore a physical expression of the pharaoh's measure, making him the eternal cornerstone of every construction. Of course, you can't run a massive construction project by having everyone measure their own forearm. The genius of the system was its physical manifestation, the cubit rod. These were not simple yardsticks. They were the sacred standard, meticulously crafted master copies often made of durable stone like granite or basalt, or from precious, stable hardwoods. They were the equivalent of the modern kilogram or meter standard kept under glass in a laboratory, but they were mobile and practical. A royal cubit rod was a masterpiece of information design. It was divided into the 7 palms, and each palm was further subdivided into the 4 digits, all clearly marked with precise incisions. But the Egyptians, in their relentless pursuit of precision, went even further. To allow for even finer measurements, they often subdivided the digit itself, creating the smallest fractions possible for the most exacting work. These rods were more than just rulers. They were complete reference guides. Many surviving examples are inscribed with the names of the pharaohs who commissioned them, granting them official authority. Some even include other useful units, like the small cubit of 6 palms used for everyday purposes, or the khet, a unit of 100 cubits used for surveying large plots of land. This ensured that from the grandest pyramid down to the most delicate piece of ceremonial furniture, every craftsman in the kingdom was working from the same exact blueprint of length. The consistency this created is nothing short of astounding. Blocks cut from quarries hundreds of miles apart would fit together with minimal adjustment because every builder, everywhere, was using a tool that was a direct copy of the same royal standard. The cubit rod was the unsung hero of Egyptian architectural perfection, the physical link that turned a theoretical system based on the body into a practical, empire-wide tool of breathtaking accuracy. While the masons and sculptors shaped the very stones of Egypt, another class of craftsmen was shaping something even more enduring: information. The true engine behind those monumental construction projects wasn't just found in the quarries or on the scaffolding. It was housed in the quiet, shaded rooms of the administration building, where the most powerful tool of all was not made of copper or stone, but of reed and wood. This was the scribe's palette, and it was the absolute nerve center of pharaonic ambition. Without this humble instrument, the pyramids would have remained a chaotic pile of rocks, and the temples, a beautiful but impossible dream. Imagine a long, thin rectangle of wood, often gracefully curved to fit comfortably in the hand. Along its top edge, you would typically find 2 shallow, circular wells for holding ink cakes, and down its center, a series of long, narrow slots to hold the scribe's most precious possession, his reed brushes. This was the complete writing kit, a portable office that held the entire bureaucracy of the kingdom in its simple form. The inks themselves were symbolic. Black ink, the standard for most writing, was made from carbon soot mixed with gum and water. But the red ink, made from red ochre, was reserved for headings, keywords, and the all-important numbers, the measurements and quantities that made construction possible. This color coding wasn't just for beauty. It was an early form of data visualization, allowing a foreman to instantly spot critical figures on a dense papyrus document. The scribe's primary role on a construction site was that of a master logistician. Before a single stone was cut, he was there, recording the pharaoh's decree and the architect's vision. He would meticulously document the final, approved dimensions of a structure using the royal cubit rod as his guide, translating the physical standard into a permanent written record. These were the original blueprints. He calculated the staggering volumes of material required, so many thousands of cubic cubits of limestone from Tura, so many hundred blocks of Aswan granite. He then drafted the orders that would mobilize the state's machinery, sending commands to quarry masters, conscripting labor from villages, and arranging for the vast flotillas of barges needed to transport it all. Once the project was underway, his palette became the tool of daily control. He kept the running inventories, tracking every block that arrived at the dock and every tool issued from the workshop. Most importantly, he managed the distribution of the most crucial resource of all, food. He recorded the vast quantities of grain, fish, and beer needed to feed the army of workers, ensuring that the payroll issued in these rations was accurate and fair. This administrative precision prevented delays and discontent, keeping the project moving smoothly. His records also served as a legal ledger, resolving disputes over quotas, workloads, and responsibilities. The smooth, precise hieroglyphs and hieratic script that flowed from his brush were the glue that held the entire enterprise together. transforming the chaotic potential of thousands of workers and millions of stones into a harmonious, coordinated effort. The scribe with his wooden pallet didn't lift a single stone, yet he was the indispensable architect of order, proving that in ancient Egypt, the most lasting structures were built not only with mortar, but with information. Yet after the brutal work of the saws and the percussive force of the chisels, the stone was still far from finished. It stood there, rough and scratched, bearing the heavy scars of its extraction and shaping. To the ancient Egyptian artisan, this was an unacceptable state. For them, a surface was not truly complete until it achieved a state of perfection that we can scarcely believe, a flawless, glass-smooth finish that could catch the sunlight and gleam like water. This transformative process, the final alchemy that turned a worked block into a masterpiece, was the domain of the smoother, and it relied on a sophisticated, graduated system of abrasion that would be familiar to any modern woodworker or metal polisher. The first step in this meticulous journey was to erase the deep grooves left by the saws and the pitted marks from the stone pounders. For this initial, aggressive grinding, they turned to rubbing stones. These were simple, hand-held blocks of an extremely hard stone like quartzite or dolerite, which is even harder than granite. Using these like sandpaper blocks, workers would rub them back and forth across the surface with tremendous effort, often aided by water or wet sand to create a slurry that accelerated the process. This was the most physically demanding phase of finishing, requiring sustained pressure to gradually grind down the high spots and major tool marks, creating a uniformly flat, though still very rough, surface. Once the worst of the scarring was eliminated, the true artistry began the gradual, patient progression through ever finer grades of abrasive. The primary material for this was all around them, sand. But not just any sand. They understood that different sands had different cutting properties. They would source specific types of sand, with quartz sand being the most valued for its exceptional hardness. The process started with a coarse, gritty quartz sand, similar to modern coarse grit sandpaper. This would be spread on the stone, often wetted down, and then workers would use flat sandstone blocks or simply their own hands, protected by leather pads, to rub the abrasive slurry in long, methodical strokes. This would remove the scratches left by the rubbing stones, replacing them with a new, finer set of scratches. And here lies the secret to their legendary finish. They never stopped at one grade. After the coarse sand had done its job, they would meticulously clean the surface and then move to a medium-grade sand, repeating the exact same process. This finer abrasive would cut more slowly, but it would grind away the peaks and valleys left by the coarse sand, creating an even smoother surface with even tinier scratches. The final step was the application of a very fine, powdery abrasive. For this, they often used emery, a natural mixture of the mineral corundum, which is second only to diamond in hardness and magnetite. This powdery paste, applied with soft leather pads or even linen cloths, was used in a final buffing stage. The incredibly hard emery particles acted as a microscopic polishing compound, erasing the last visible scratches and bringing the stone to a high, reflective sheen. The evidence of this painstaking, multi-stage process is everywhere. Run your hand carefully over the interior of a granite sarcophagus in a museum, and you can still feel the impossible smoothness, a surface so flawless it feels almost soft. Look at a statue of a pharaoh, and you can see how the light glides over the polished curves of the stone. This wasn't merely for aesthetic vanity, it held deep symbolic meaning. In a culture that believed the gods themselves had skin of gold and bones of silver, a highly polished surface that reflected light was the closest a craftsman could come to making stone divine. It captured and played with the sunlight, making the statues seem alive and radiant, as if imbued with a celestial energy. This relentless pursuit of the perfect finish, a process that could take months for a single object, demonstrates that for the ancient Egyptians, true mastery was found not in the grand strike, but in the final, whisper-soft touch. Yet for all their mastery of flat planes and vertical lines, the ancient Egyptians faced a geometric challenge that was absolutely fundamental to their entire architectural vision: the perfect right angle. Their world was built on squares and rectangles from the base of every pyramid to the layout of every temple courtyard. A structure that was level and plumb could still fail catastrophically if its corners were not true 90-degree angles. The tool they used to guard against this was a masterpiece of simple, undeniable geometry, the L-shaped square. This seemingly basic instrument was, in fact, one of the most critical devices in their entire toolkit, a physical guarantor of structural integrity and aesthetic perfection. The design was brilliantly straightforward. Picture two straight-edged rules, likely made of wood for most carpenters or stone for master builders setting out monuments, fixed securely together to form a perfect right angle. There was no room for approximation. The integrity of the entire tool relied on the absolute precision of that 90-degree corner. To use it, a craftsman would simply place the inside of the L against a corner he had cut or built. Any gap between the tool and the workpiece immediately revealed an error. If light showed between the square and the stone along the vertical edge, the angle was too acute. If the gap was along the horizontal, the angle was too obtuse. This immediate visual feedback allowed for instant correction. It was a tool of pure verification, a yes or no test that left no room for doubt. Its importance simply cannot be overstated. In woodworking, the L-square was the key to creating strong, lasting joinery. A chair, a chest, or a bed frame assembled with imprecise angles would be wobbly, weak, and prone to collapsing under stress. The square ensured that mortise and tenon joints would fit together with snug, powerful precision, creating furniture that could last for centuries, as the stunning examples from Tutankhamun's tomb so beautifully prove. In masonry, the square was used to set out the corners of buildings and to check the shape of individual blocks as they were dressed. A pyramid built from blocks with even slightly irregular angles would have resulted in sloping, uneven walls and misaligned courses that would compromise the entire structure's stability. Perhaps the most stunning evidence of their success with this tool is found in the most sacred of objects, the granite sarcophagus. These massive coffins, carved from a single block of incredibly hard stone, are marvels of precision engineering. Their corners are not just approximately square, they are mathematically perfect right angles, and their opposing sides are perfectly parallel. The inside surfaces are often so smooth and flat that the lid, another monstrous slab of stone, fits with a seal so tight that not even a razor blade could slip between them. This astonishing precision, achieved on a scale of tons of granite, starts with the simple, unwavering truth of the L-shaped square. It was the first and most important check in a long process of refinement, the foundational truth upon which all other perfection was built. In a world without digital protractors or laser guides, the L-square was their anchor to geometric certainty, a humble tool that ensured the corners of their world were as strong and perfect as their ambitions. While the delicate adze and the precise bow drill shaped the finer details of Egyptian woodworking, the first step in taming the forests along the Nile was a far more brutal and monumental task. This was the domain of the hewing axe, a tool of raw power designed not for subtlety, but for the initial conquest of nature itself. Before a single elegant hull could be carved or a palace beam could be set in place, someone had to venture into the groves of acacia, tamarisk, and the prized sycamore fig trees, and bring them down. The hewing axe was the primary instrument of this formidable undertaking, a heavy-duty implement that transformed living wood into a manageable resource. The design of these axes was a direct response to the limitations of their materials. Unlike the hardened steel axes of later eras, Egyptian axes were crafted from copper or, in later periods, bronze. These metals are relatively soft and can bend or dull quickly when striking resilient wood. To overcome this, Egyptian axe makers developed a brilliant solution. They mounted the metal blade in a way that minimized direct impact. The blade itself was not a single, solid piece with a hole for the handle like a modern axe. Instead, it was a flat, crescent-shaped piece of copper that was lashed tightly into a V-shaped notch at the end of a heavy, stout wooden handle using wet leather thongs or sinew. As the leather dried, it would shrink, creating an incredibly secure hold. This design meant that the shock of each blow was absorbed primarily by the wooden handle and the lashings, protecting the softer metal blade from deforming. The weight of the swing came from the dense wood of the handle itself, turning the entire tool into a powerful, percussive hammer with a sharp cutting edge. Felling a large tree with such a tool was an act of immense stamina and coordinated effort. A team of woodcutters would take turns, their axes rising and falling in a steady rhythm. They wouldn't simply chop straight through the trunk that would quickly trap the blade. Instead, they used a technique of cutting alternating downward angled notches on opposite sides of the tree, creating a deeply grooved waistline. The sound would have been a constant, dull thwack of metal biting into fibrous wood, not the sharp crack of a steel blade. It was slow, exhausting work, and the axes would require constant resharpening by a nearby smith. But eventually, the great tree would groan, splinter, and crash to the earth. Once felled, the hewing axe's work was far from over. The branches had to be lopped off, and the irregular log had to be transformed into a square, usable beam. This process, called hewing, is where the tool truly earned its name. The log would be rolled onto a stable platform, and woodcutters would use their axes to literally chop away the rounded sides. They would often score guide lines along the length of the log, and then methodically hack away everything outside those lines, creating a rough, faceted surface that could later be refined with adzes. The amount of sheer physical strength required for this entire process is almost unimaginable. It was a battle of attrition against the wood, powered by muscle, patience, and the relentless, percussive force of the hewing axe. This tool was the essential gateway that turned the raw bounty of the Nile's banks into the foundational material that built their ships, their roofs, their furniture, and their chariots, proving that their civilization was forged not just with intellect, but with tireless strength. While the hewing axe and the adze were masters of shaping wood's outer form, the true soul of Egyptian woodworking, the element that gave their creations both strength and immortality, lay hidden within the joints themselves. This was the domain of a highly specialized and utterly critical tool, the mortised chisel. In a world without industrial nails or screws, the entire structural integrity of everything from a simple stool to a royal chariot depended on the ancient art of joinery. The mortised chisel was the key that unlocked this art, a tool engineered for one specific, vital purpose: to cut clean, deep, square holes known as mortises. Its design was a significant departure from the standard woodworking chisel, where a typical firmer chisel had a blade that was relatively wide and thin, designed for paring and shaping. The mortised chisel was built for power and punishment. Its blade was stout and thick, often nearly as thick as it was wide. This robust construction was absolutely essential because it acted as a lever within the cut itself. As a carpenter drove the chisel deeper into the wood to excavate the mortise, the thick blade could withstand the tremendous sideways pressure and torsional forces without bending or snapping. The handle, too, was built to endure. It was frequently reinforced with a leather or metal collar at the top to prevent it from splitting when struck repeatedly by a mallet. This was a tool designed not for finesse, but for controlled, percussive excavation. The process of creating a mortise and tenon joint was a meticulous dance of precision. First, a carpenter would carefully mark out the precise location and dimensions of the mortise hole on the workpiece. Then, using a bow drill with a bit roughly the width of the mortise chisel, he would drill a series of overlapping holes along the length of the marked-out rectangle. This wasn't strictly necessary, but it was a brilliant labor-saving technique. It removed the bulk of the waste wood, making the chisel's job far easier. Now the mortised chisel came into its own. The carpenter would place its sharp, squared-off edge at the perimeter of the hole and strike it with a wooden mallet. Instead of slicing the wood, he would use the chisel to lever out small chunks, slowly and methodically squaring up the round drill holes into a perfectly rectangular socket. He would work his way along the length of the mortise, frequently checking for depth and squareness with a ruler or a marked rod, ensuring the walls were straight and the corners were sharp 90-degree angles. The result of this painstaking work was a joint of incredible strength and longevity. Into this clean, square mortise, the craftsman would then fit a tenon, a protruding tongue carved on the end of another piece of wood, shaped to match the mortise exactly. When tapped into place, often with a dab of animal glue for added security, the interlocking parts created a bond that was far stronger than the wood around it. This is the single greatest reason why we can walk into a museum today and see chairs, beds, and chests from Tutankhamun's tomb that look like they could still be used. The nails we rely on today rust, weaken, and loosen over centuries. The ancient Egyptian joint, carved with the mortise chisel, does the opposite. It holds firm, distributing stress evenly and allowing the wood to move slightly with changes in humidity without breaking apart. This tool didn't just make furniture, it engineered a legacy, ensuring that the exquisite craftsmanship of a royal carpenter would stand the test of time. A silent testament to a joinery technique so advanced it has never truly been improved upon, only replaced. While the massive saws and heavy mallets captured the dramatic force of Egyptian construction, some of their most critical work began with the lightest and most precise of touches, a simple poke from a sharp, hardened point. This was the realm of the awl, a tool so modest in appearance it could be easily missed, yet so fundamental to accuracy that without it, the entire enterprise of Egyptian craftsmanship could have descended into chaos. In a world where a misplaced drill hole could ruin a priceless piece of jewelry, or a misaligned scribe line could throw off the entire corner of a building, the awl was the first and most important guarantor of perfection. Imagine an artisan preparing to drill a hole in a piece of ebony for an inlay or through a sheet of gold for a pectoral necklace. A bow drill with a copper tip would be almost impossible to start precisely by hand. The bit would skitter across the hard, smooth surface, scratching it and likely starting in the wrong place. The awl solved this. The craftsman would first position the sharp, needle-like point exactly where he wanted the center of the hole to be. With a gentle pressure, often just from the palm of his hand, he would twist the awl back and forth, cutting a small, conical depression called a pilot hole. This tiny indentation acted as a perfect guide, capturing the tip of the drill bit and holding it firmly on course as the bow was drawn back and forth. This ensured every hole was drilled exactly where intended, preventing costly mistakes and wasted materials on some of the most valuable objects in the ancient world. But the awl's role extended far beyond just starting holes. It was also the primary tool for scribing, the process of transferring a design from a papyrus plan onto a blank piece of wood, stone, or metal. An architect's drawing of a hieroglyphic inscription or a decorative border was useless unless it could be accurately copied onto the workpiece. The craftsman would lay the plan over the material, and then, using the awl like a pencil, he would carefully trace over the lines, pressing down just enough to scratch a faint but permanent guide into the surface below. For stone carvers, these scratched lines were the absolute blueprint they followed with their chisels. A single misplaced line from an awl could result in a misspelled word or a botched symbol, an error that would be literally set in stone for eternity. The awl gave them the confidence to begin the irreversible process of carving, knowing their first mark was true. The design of the tool was a lesson in focused efficiency. Most were little more than a sharp, hardened copper or bronze point set into a comfortable, often bulbous handle made of wood or bone. There were no moving parts, no complex mechanics, just a perfectly sharpened point designed for maximum control. The best awls were likely heat-treated to harden the metal, allowing the tip to stay sharp even after repeatedly scoring tough materials like limestone or hardwood. This combination of a sharp point and a handle that fit snugly in the palm gave the craftsman exquisite control, allowing for lines of hair-thin accuracy. In the hands of a master, the awl was not just a tool, it was a precision instrument. It was the unsung hero of the workshop, the quiet implement that spoke the first word in every project, ensuring that every cut, every drill, and every carve that followed would contribute to a flawless whole. A testament to a civilization that understood that true greatness always begins with getting the small details right. But before the first awl mark could be made or the first chisel strike could fall, every monumental project in ancient Egypt began not with stone, but with thought. It started as a vision in the mind of a pharaoh or his master architect, a concept that needed to be translated from abstract idea into buildable reality. For this crucial act of creation, the most important tools were not made of copper or stone, but of the most humble materials the Nile provided, a broken piece of pottery and a frayed reed. The marriage of the ostracon and the reed brush formed the ancient designer's sketchpad, offering us a priceless window into the brilliant minds that planned these timeless wonders. The reed brush itself was a marvel of minimalist design. A craftsman would simply take a single stalk of the common reed, Juncus maritimus, and chew on one end or gently crush it with a stone. This would separate the soft, pulpy fibers, transforming the rigid stem into a delicate, flexible brush tip, not unlike the watercolor brushes used by artists today. This prepared tip could then be dipped into ink, a simple mixture of water, gum, and either carbon for black or ochre for red, and put to work. The variety of line this simple tool could produce was astonishing. With a light touch, it could draw a hair-thin guide line for a hieroglyphic inscription. With more pressure, it could lay down a bold, confident stroke to outline the massive flank of a pyramid or the column of a temple. The reed brush was the direct conduit from the architect's hand to the medium, capable of both fine detail and grand, sweeping statements. That medium was often not precious papyrus, but something far more common and practical, the ostracon. These were simply broken fragments of pottery or flat flakes of limestone that littered every settlement and workshop. For an architect or draftsman, these discarded shards were the perfect scrap paper, durable, abundant, and free. They became the testing ground for ideas, the place where genius worked through its problems. Surviving ostraka reveal every stage of the creative process. We have found quick, proportional sketches of temple facades, where a master is working out the spacing of columns. We have meticulous practice drawings of hieroglyphs, where a skilled hand is rehearsing the perfect form of a symbol before committing it to a tomb wall for eternity. We even see humorous doodles and caricatures, reminding us that these were real people with a sense of humor, not just anonymous cogs in a machine. Perhaps the most breathtaking examples are the detailed architectural plans. One famous ostracon, for instance, shows a precise, scaled design for the complex, curved ceiling vault of a tomb. The draftsman has used a grid of red lines to maintain perfect proportions, a technique that allowed him to scale his idea up to its full massive size. This was not a vague idea, it was a working blueprint. Another incredible find is a grid-based drawing of a royal statue, used as a guide for teams of sculptors working on different sections simultaneously. The grid system ensured that everyone was working from the same master plan, guaranteeing that the final, colossal statue would be perfectly proportional from every angle. These sketches reveal a level of pre-planning and mathematical foresight that completely shatters the old image of ancient builders working from rough ideas alone. The true magic of the reed brush and ostracon lies in what they represent, the democratization of the creative act. While grand visions came from the pharaoh, the practical execution was in the hands of these master designers. Their shards of pottery capture the moment of inspiration, the correction of a mistake, the refinement of a curve. Each line drawn with a reed brush was a decision made, a problem solved, a step closer to immortality. These tools were the birthplaces of the monuments we marvel at today, proving that the greatest structures in human history began not with a mighty blow, but with the gentle, deliberate scratch of a reed brush on a piece of broken pot, a quiet testament to the power of a plan. While the bay level was the master of the artisan's immediate workspace, ensuring a single stone was flawlessly flat, the Egyptians faced a far grander challenge: how to enforce that same perfect level across the vast, undulating landscape of a construction site spanning dozens of acres. The foundation of the Great Pyramid alone covers an area equivalent to nearly 10 football fields. How could they possibly ensure that every single corner of this massive limestone platform was on the exact same horizontal plane, with an error margin of less than an inch? The answer lies not in a complex machine, but in one of the most fundamental forces of nature: harnessed with breathtaking ingenuity. They used water itself as their ultimate ruler. This technique, known as a simple water level, is a concept so straightforward it feels almost obvious, yet its application on such a monumental scale is a stroke of pure engineering genius. The principle is one that anyone can test in their backyard. Water, when at rest in an interconnected body, will always seek to level itself. The surface of a still pond is perfectly flat. The ancient Egyptians applied this universal law of physics to their construction sites by digging a network of shallow trenches across the entire area, destined to become a pyramid's foundation. These trenches were then carefully filled with water, creating a sprawling, temporary web of canals. Now imagine the scene. Workers would place tall, marked stakes into the water at regular intervals across this entire network. Because the water's surface in every connected trench was level, the top of the water would touch each stake at precisely the same height. By marking a line on every stake at that exact water line, the Egyptians created a permanent, site-wide grid of reference points, all sharing an identical elevation. A mason working on a block hundreds of meters from the center could simply measure down from the mark on his nearest stake to know exactly how high or low his stone needed to be to match the master plane. This system turned an impossibly complex surveying problem into a simple exercise in measurement, democratizing precision for every worker on the site. The potential applications for this technology extended far beyond the sacred plateau of Giza. One of the most grueling and continuous civil engineering projects in ancient Egypt was the maintenance and excavation of canals off the Nile. These waterways were the lifeblood of the kingdom, crucial for irrigation, transportation, and flood control. For a canal to function properly, it required a very slight, consistent gradient, allowing water to flow slowly and steadily from the river to the fields without either stagnating or rushing through with destructive force. Achieving this gentle, uniform slope over distances of many miles would be a formidable task even with modern laser levels. The Egyptians almost certainly used the same water trench method. By digging a shallow pilot canal and filling it with water, engineers could check the water's depth at countless points along its length. Anywhere the water was too deep indicated a dip that needed filling. Anywhere it was too shallow indicated a hump that needed digging out. This method provided a continuous, real-time feedback loop, enabling them to sculpt the landscape with a hydraulic precision that ensured the life-giving waters of the Nile could be distributed evenly and efficiently across the entire kingdom. This humble technique, using little more than ditches and water, showcases a profound understanding of natural principles, transforming a simple observation of physics into the bedrock of an empire's infrastructure. But perhaps the most dramatic and least understood application of fire wasn't for creating small holes, but for moving entire mountains. We've explored the incredible precision of their saws and drills, but that still leaves a monumental question unanswered. How did they initially separate these colossal blocks, some weighing hundreds of tons, from the living bedrock of the quarries? Some of the tool marks we find point to a technology far more elemental and powerful than any copper chisel: the strategic and brilliant use of fire itself. There's compelling evidence to suggest that Egyptian quarry masters were true masters of pyrotechnology, using heat as a devastatingly effective wedge to break stone on a gigantic scale. Walk through the granite quarries at Aswan today, and you'll see more than just the chisel marks from the unfinished obelisk. Look closer at the trench walls and the floors of the quarries, and you'll find long, deep fissures and vast, curved scars on the rock faces. These aren't the straight, deliberate cuts of an abrasive saw. These are the chaotic, explosive fractures of stone that has been subjected to tremendous thermal shock. The theory, supported by many geologists and archaeologists, is that workers used a technique called fire setting. They would build small, controlled fires directly against the granite surface along a predetermined line where they wanted the block to separate. They would keep these fires burning for hours, steadily heating the stone. Granite, like all rock, expands when heated. This intense, localized heat would create massive stress within the stone, causing microscopic cracks to form and propagate. Then, at the precise moment when the rock was at its most stressed, workers would douse the blazing hot surface with torrents of water, likely from the Nile just meters away. The rapid, violent cooling would cause the outer layer of stone to contract explosively, while the inner core remained expanded. This incredible differential would rip the rock apart along the weakened line of the fire, shearing off huge slabs and blocks with a sound that must have been thunderous. This wasn't a gentle process. It was a controlled demolition using the fundamental forces of physics. The fire did the brutal work of fracturing, and then the teams with their stone pounders and chisels could move in to precisely define and undercut the block, refining the rough, fire-broken surface into something that could be transported and finished. This technique elegantly explains some of the most puzzling evidence at quarry sites. Those vast, curved scars on the quarry walls are the classic spall marks left behind when a large, concave section of rock shears off from thermal shock. The piles of charcoal and ash found in and around ancient quarries, once thought to be merely from workers' campfires, take on a new significance as the possible remnants of this industrial process. Fire setting would have been an immensely efficient way to initiate the quarrying of the largest blocks, saving an incalculable amount of time and labor compared to trying to pound an initial trench entirely by hand. It reveals a sophisticated understanding of material science, an intuitive grasp of how different materials react to extreme changes in temperature. The Egyptian quarry worker, therefore, wasn't just a laborer with a hammer. He was a technician wielding one of the most powerful and unpredictable elements on Earth, harnessing its destructive fury to literally reshape the continent for his pharaoh's ambition. Yet for all the monumental tools of stone and wood, one of the most intimate and versatile instruments in ancient Egypt was also one of the smallest, the copper needle. This unassuming sliver of metal, so easily overlooked in the shadow of massive saws and obelisks, played a role that spanned from the most mundane tasks of daily survival to the most sacred rituals of the afterlife, proving that a tool's significance is measured not by its size, but by the breadth of its purpose. In the bustling workshops and humble homes along the Nile, the needle was an essential implement for creating and maintaining the very fabric of society. Sailmakers relied on sturdy, large-eyed needles to stitch together the massive linen sails that harnessed the wind for ships traveling the Nile and the open sea. Each sail was a masterpiece of durability, its seams sewn with such strength that it could withstand the punishing forces of a Mediterranean gale. In the home, women used finer needles to weave and repair clothing, from the simple linen kilts of laborers to the pleated, transparent gowns of the elite. The quality of the needle directly influenced the quality of the stitch. Egyptian needle makers displayed remarkable skill in their craft, taking a soft copper wire, hammering one end to a sharp point, and then painstakingly drilling a tiny, precise eye at the other end. This was a feat of miniaturization that required incredible patience and a steady hand, likely achieved with a bow drill and a fine abrasive paste. The result was a tool that could guide linen thread through fabric with minimal resistance, allowing for the tight, even stitches we can still see on preserved textiles from tombs. This was not a disposable object. A good copper needle was a valuable personal possession, carefully stored and passed down, its value lying in its ability to create, mend, and sustain the material world. But the journey of the copper needle did not end in the land of the living. It held a sacred and solemn duty in the realm of the dead, where it became an instrument of transformation in the hands of the embalmer. The process of mummification was a lengthy, ritualized dissection aimed at preserving the body for eternity. After the internal organs were removed and the body was dried with natron salt for 40 days, it was left in a severely desiccated and fragile state. The final, crucial act of physical restoration fell to the embalmer and his needle. Using a large, curved copper needle much like a modern surgeon's suture needle, he would carefully stitch the body back together. Long incisions, such as the one made in the left side to remove the organs, had to be closed securely. The embalmers employed a distinctive and strong stitch, often a crisscross pattern or a simple running stitch, that pulled the skin taut and sealed the body's sacred vessel. This was not merely a functional act, it was a deeply symbolic one. Each stitch was a step towards reconstituting the physical form, making the body whole and perfect again for its journey into the afterlife. The needle, in this context, transcended its physical form. It was no longer just a tool for joining cloth, but an instrument of ritual closure, weaving the mortal coil back together in preparation for its eternal existence. The same basic technology that repaired a torn sail on a boat was used to suture the very vessel of the soul, showcasing a profound unity between the practical and the spiritual that defined every aspect of ancient Egyptian life. So where did all of these incredible tools go? Why, for so long, did we picture the ancient Egyptians as primitive laborers instead of the master engineers they truly were? The story of their disappearance is a quiet tragedy of time, material, and shifting historical focus, a legacy that was quite literally lost to the dust. The first and most obvious reason is the simple ravages of time. Consider the composition of their toolkit. For every durable copper chisel or bronze adze blade that might survive, there were a dozen organic components that have long since crumbled into nothing. The meticulously carved wooden handles of their mallets, the elegant L-shaped frames of their bay levels, the long, straight wooden guides for their massive abrasive saws, the reed brushes, the cubit rods, all of these were made of wood, reed, or leather. In Egypt's climate, these materials only survive under the most extraordinary conditions, like the absolute dryness of a sealed tomb. The vast majority of tools, those used daily in dusty workshops and sun-baked quarries, simply wore out, broke, and were discarded, their organic parts decomposing completely, leaving behind only the most durable metal components, which tell just a fraction of the story. Then there was the powerful culture of recycling. Metal was always a valuable and finite resource in ancient Egypt. Copper and bronze were not disposable, they were commodities. When a chisel became too short from constant resharpening, or a saw blade cracked, it wasn't thrown on a scrap heap. It was gathered up and sent back to the smelter. The metal would be reheated, recast, and reforged into a new tool, a weapon, or a piece of jewelry. This endless cycle of reuse means that the vast majority of metal tools ever created were ultimately destroyed to make something else. The evidence we have today, the few pristine chisels found in foundation deposits, or the rare adze blade left in a tomb, are the exceptions. The ceremonial items deliberately spared from this cycle. The countless thousands of workaday tools that built the pyramids were almost certainly consumed by it, their metal living on in other forms, their original sophistication melted away. Perhaps the most profound reason for our ignorance, however, lies in the lens through which later civilizations, and indeed early archaeologists, viewed history. The classical world of Greece and Rome, with its extensive written philosophies and its more familiar-looking architecture, has long been held up as the cradle of Western engineering and science. Their achievements were celebrated and well documented in texts that European scholars could read and admire. This created a historical bias, a narrative that often traced a direct line from classical antiquity to the modern world, inadvertently skipping over or diminishing the contributions of earlier cultures like Egypt. For a long time, when Western archaeologists first arrived in Egypt, they saw the pyramids and temples as marvelous curiosities, but they often assumed the methods used to build them must have been the same primitive ones described by later Greek historians like Herodotus, who wrote about ramps and levers but had no first-hand knowledge of the actual techniques used millennia before. The sophisticated technology of the Egyptians was not just forgotten, it was never really looked for, obscured by the shadow of later empires. Thankfully, that story is now changing dramatically. The field of archaeology has moved far beyond just treasure hunting for gold and mummies. Modern archaeologists are detectives of the mundane, and it is in the quiet analysis of the seemingly insignificant that the truth is re-emerging. They don't just look for the tools themselves, they search for the subtle fingerprints these tools left behind. They perform microscopic analysis on the cut marks in granite sarcophagi, identifying the specific grit of the quartz abrasive that made them. They create silicone casts of drill holes in stone to study the unique spiral grooves that reveal the feed rate and rotation speed. They examine the wear patterns on the few surviving metal blades to understand the exact angle and force with which they were used. And they increasingly experiment with replicative archaeology, trying to rebuild and use these tools themselves. It is through this painstaking, quiet work, this conversation with the stone itself, that we are finally listening to the ancient craftsmen. We are beginning to hear the stories their tools have been whispering all along. Stories not of brute force, but of breathtaking intelligence, patience, and a forgotten technological prowess that is only now stepping back into the light. From the celestial ambition of the merkhet, which anchored their temples to the cosmos, to the earthly certainty of the plummet and bay, which ensured their walls rose true and their foundations lay perfectly flat, the ancient Egyptians engineered a world of precision with an array of tools that were nothing short of revolutionary. We've journeyed from the massive, groaning abrasive saws that conquered granite with relentless patience, to the delicate bow drill that could start a cooking fire or perform intricate dental work. We've seen the hewing axe that felled mighty trees and the mortised chisel that joined them into eternal furniture, the sacred adze of Ta and the humble all that ensured every first mark was perfect. Each tool, from the grandest to the most modest, was a testament to a profound understanding of physics, material science, and geometry, a solution forged from necessity, refined by intellect, and executed with unwavering patience. This was not a civilization that relied on alien technology or impossible magic. Their true power was human ingenuity, amplified by a culture that valued precision, planning, and the divine nature of skilled craftsmanship. They looked at a block of stone harder than steel and didn't see an obstacle. They saw a puzzle to be solved with sand, water, and copper. They looked at the night sky and saw not just gods, but a perfect clock and a compass to guide their most sacred structures. They were the ultimate makers, and their toolkit was their greatest invention. The next time you see a photograph of the pyramids or walk through a museum gallery past a serene stone statue, I urge you to look closer. Don't just see the monument, see the tool marks. See the flawless polish that took months of rubbing, the perfectly drilled hole that started with a pilot point, the seamless joint that is held for millennia. See the clever hands that held the merkhet, the mallet, and the brush. These forgotten tools were the true builders of a civilization that continues to awe and inspire us, and they whisper a powerful truth, that human curiosity, when applied with relentless determination, is the most powerful technology of all. If you've enjoyed this deep dive into the workshops of the pharaohs, make sure to subscribe and hit the bell, because we're just getting started uncovering history's hidden technologies.